better. Yeah. Okay. Great. All right. So I'm going to talk about specific instances of the following sort of question: how many curves of genus G and degree D on a, well, say pass through say M points in a space X. This is an overarching question. It's been studied a lot in many different contexts. And I want to sort of look on a very, very concrete example of this to make sure that, well, please stop me if anything I said, everything I say from now on is unclear. I really like the interactive type of thing, so I know it's hard in Zoom, but stop me anyway. So what does this mean more concretely? So today we're going to basically focus on the case G equals 0. Okay, and that's what we call rational curves for reasons that will soon become evident. First, well, for starters, let's consider the case that that we look at the space X is just equal to the n-dimensional space over the complex numbers. Okay, and then what do we mean by a genus 0 curve, a rational curve? So well, that's the same thing as a map from an open subset of C. Let's say, actually, it's just going to be equal to C minus a finite set. To Cn, which is going to be given by a bunch of polynomials, so rational functions. So we'll have P1 of Z over P0 of Z up to Pn of Z over P0 of Z. And so this is the definition of a rational curve. And here P 0 up to Pn are polynomials and the maximum of the degrees of the Pi is equal to D. And let's assume they don't have any common factors. So there's no polynomial of lower degree which divides all the P0 up to Pn. Okay, so that's a rational curve of degree D. And we have to define an appropriate notion of equivalence. So equivalent, so equivalence. So we say that F and G, so F, let's say from U to Cn, G from V to Cn, the rational curves are equivalent. And we're going to say F twiddle G that is given by if there's a Mobius transformation u to v, so phi of z is equal to a z plus b, c z plus d. Maybe I should have said something here. Right, maybe I want to make this a tiny bit more explicit here. Actually, it's not so important. Right, so I should mention that these, okay, let's not get to the, right, so if there's a phi from u to v such that f is equal to g composed with phi. Okay, that's an equivalence relation. So, yeah, I hope that Howie has shared with everybody, there's like a link to this notebook in case you ever want to look back at something I said before. Howie, were you able to share that with everybody?
Yeah, I shared that.
Great, wonderful.
It's
Thanks
in the chat.
a lot. Wonderful.
And I'll email it after as well.
Thanks a lot. Okay, so here we have a notion of rational curves up to a certain equivalence relation. And now we can really ask our question, which is, so let's make this a little bit more specific. We'll call it Q prime. And that's going to be, so how many rational curves of, right, so this is a rational curve of degree d, right? And d is just a maximum of the degrees of the polynomials. How many rational curves of degree d pass through say m points in Cn. Okay, so that's a bit of a down-to-earth question. And let's do some examples to get a feeling for this. Let's suppose that, so rational curves, when I say rational curves, I should say up to equivalence, right? So the example here is that let's consider d equals 1. Okay, so then up to equivalence, we can assume that p0 is just equal to the constant function. So we can make that simplifying assumption. So then basically f is just going to be equal to p0 of z, p1 of z up to pn of z, which is just going to be a linear function. So of course, that's just a line. So like f is just a line. And well, if we consider m is equal to 1, then, well, there's an infinite number of lines passing through a point. And if we consider f equals to 3 or more, then there's, assuming that, let's say, let me give these points some names just for convenience. Let's say x1 up to xm. So if for basically, we're going to get 0. If you have 3 points which are not collinear, so let's say 0 for almost every collection of x1 to xm inside of the space C n times itself m times. So as long as you're not in a set of measure 0 and the M self product of Cn, then you always get 0 because the points won't be collinear except for in measure 0. And then for m equals 2, we all know that there's a single unique line through any 2 points, as long as again a measure excluding a set of measure 0. Okay, so that's a fairly down to earth example. Next example would be, let's say, let's specialize in n equals 2. It's easy to get a feel of. Let's say d equals 2 now. So you can show, it's elementary to show that a rational curve is a conic section. So if you look at the image of such a map, you get a conic section. So that's to say an ellipse, hyperbola, or parabola. And then now if we have m is equal to, should I say 4 or less, then what turns out is we get an infinite number of conic sections through 5 points, through 4 points or less, conic sections through m points. And if we have m is greater than or equal to 6, we get none. Again, I'm assuming, aside from a set of measure 0, I'm gonna not repeat that too many times. And when n equals 5, I get exactly 1. Okay, so we see a pattern here. The general case is, and this is again elementary, that the number of there will be the rational curves of degree d through m points is finite and need not be 0 if and only if let's say Cn is finite and need not be 0 if and only if n plus 1 times d plus 1 minus 4 is equal to n minus 1. Let's say just divide by that, n minus 1 m. Okay, so this is, again, it's just you count the number of degrees of freedom, how many coefficients of polynomials you have, how many symmetries you have, and you get this thing. And then the question is, so, this is kind of the boring part of the story. You define nd, let's say nc is equal to, let's call this m of n and d. The number of rational curves of degree d through m and d points in Cn. Okay, so this is now need not be 0 or infinity. Still not so interesting. So let's do an example. This is going to be the example of n equals 2. And this example has a long history. So let's do d versus m of nd, which by just substituting in this formula above you just is 3d minus 1. Whoops. I should have said this. M of nd is equal 3d minus 1. And then we have nd to c. And we just said that in the case when degree is 1, that's lines through 2 points. There's a one of them. And if the degree is 2, that's conics through 5 points. And again, it's elementary linear algebra essentially to show that there's one of them. Now, when you do 3, when you do rational curves of degree 3 through, well, 3d minus 1 now is 8 points, then the answer turns out to be 12. And so let's say this was done by the Greeks, roughly speaking. And when you do through rational curves of degree 4, the answer turns out to be 620. So this stuff was known to a German mathematician, Zeuthen, from 1870. And then nothing was made, no progress was made on this problem for over 100 years. And finally, in 1994, roughly speaking, but maybe the ideas started to formulate themselves in 1985, you had somebody came up with the 87,304, and in fact, all the subsequent numbers in this series. So this was, I guess, work of Gromov and Witten, and I think the person who actually wrote down these numbers was Kontsevich, and that went along with work of, well, I guess that also appeared in work there with Manin, and there was also sort of essentially subsequent, what do you call it? Simultaneous papers of Rahn, Tian, McDuff, Solomon, not this Solomon, but rather Dietmar Salomon. And this was, I say, roughly 1994. Okay, so this was sort of the whole for arbitrary degree. Okay, and in fact, what they did works for arbitrary n too. And sort of the key ingredient here is what you call the WDVV equation. So that stands for Witten, Digraph, Verlinde, and Verlinde. The Verlinde brothers are some physicists, apparently twin brothers, both string theorists. Anyway, this is the story of this problem over the complex numbers. So,
so they have a closed formula for this number?
Yeah, so there's a recursion formula. So this basically gives you a recursion. Thanks for asking. This is a recursion formula for the ND NC. Yeah, so you just get, it's a sort of a nonlinear, it's a quadratic recursion formula.
Is there a catchy name for this number or just ND?
Oh, I don't know. There's a really catchy name for them. I guess you call them Gromov-Witten invariants of the projective space of dimension n. So I mean, I would call them Gromov-Witten invariants. Although, I guess people understood. So I mean, this leads to, which is maybe why I mentioned Gromov-Witten. But I mean, so these numbers were understood by people like, you know, over 100 years ago, 150 years ago by this point, right? So, so I don't know if it's fair to call them. I mean, so the natural generality of these numbers is much greater, and in that case, really, the definition is due to Gromov and Witten, and maybe some other people too. Ron, Tian, McDuff, Salomon, Konsevich, and so on. But I mean, in this case, still, it's an extremely difficult problem to compute these numbers, and somehow looking at things in the general context really makes it accessible. And so I'm not going to say exactly what this WDVV equation is now because I want to get on to a bit more recent work. Keep an eye on the clock here. Okay, so I mean, maybe when I say Gromov-Witten invariance, you ask, what do you mean invariance? So this is sort of an important point to make here, that actually, I mean, it's not entirely obvious, though it's not super hard to see. But I mean, for this whole discussion to make sense, it's important to notice that sort of this N, D, and C doesn't depend on the choice of the points that in Cn that you have to pass through. Okay, so there's different ways of thinking about this. One way you can think about it is that somehow like the complement of that bad set is connected and you can just move around in it, and so sort of you can connect any 2 points and any 2 configurations of M points, I should say, and then somehow this number stays constant. But maybe a sort of a more modern way of looking at it would be to say that so this is what we mean by invariant, right? So I mean, it doesn't depend on the points that you choose. It only depends sort of on the geometry of the space Cn, in a sense. Of course, you could have more complicated spaces, and then you'd get interesting information about the space from looking at these numbers. And for example, you could use them to distinguish between different spaces. For example, if you're trying to classify symplectic manifolds or something like that. So the reason that this thing is invariant, like a sort of more modern approach, would be that N, D, and C is the degree of the map. So you have, let's say, M0, M, D. This is going to be a space of, so degree, I mean the Brouwer degree. So if you have a map between two, I'm going to spell it wrong, alas. If you have a map between 2 manifolds of the same dimension, you look at the number of inverse images of a given point, a generic point, and that number is going to be independent of which point you take, roughly speaking. So this M0MD is going to be the space of n plus 1 tuples of f and z1 up to zm, where f is a rational curve of degree d, and z1 up to zm are points in C, let's say distinct, up to, up to Mobius equivalence. And then you can map this space to Cn times itself m times. And the map is going to take this tuple to f of z1. I mean, I'm gonna have to, it's gonna be defined on some appropriate subset, but I mean, that's not really super important here. Like so. And so if you just look at the inverse image of a generic point here, you're going to get exactly n, d, and c points over here in this space M0M. And secretly, you do have to if you want to really make sense of this using degree, it's important that when you compute the degree of a map, the map actually has to be a map of, at least in the classical context of smooth topology, you want to look at the map of closed manifolds, compact manifolds without boundary of the same dimension. So these guys have the same dimension by the fact that you're looking at m equals m. So these are the same dimension. Let's write this down. So these are the same dimension. Right, these are two manifolds of the same dimension because m and m equals m of nd. That's exactly what that formula m of nd was, just to assure that these things have the same dimension. Well, without going into the details, you can compactify. This is one of Gromov's key insights. And and this, of course, you can compactify. That's basically the idea of projective space. This is kind of Gromov compactness, if you wish. And these spaces, when you compactify, they are all nice and orientable and smooth and so on and so forth. So all right, so then you can look at the degree of this map, and it's well defined as topological invariant. Doesn't have anything to do with which points you choose. Okay, so question prime. What happens if we consider just like question prime, but replace C with R? Okay, so I mean, secretly, C was coming up in various places here. So for example, if you go up and you look at these polynomials, so of course, the natural thing to do here is to look at C. Pi of z is equal to sum aij z to the j equals 1 to d, 0 to d, where the aij belong to C. Okay, so C was in Cn, C was in the coefficients of these polynomials, C was in the Mobius transformation. A, B, C, and D were complex numbers. C was all over the place, but you can now just replace C everywhere with R and try to ask the same question. So what happens? We have a problem. The problem is that that it's no longer true that, so the naive definition, if you just count the number of if you just count the number of real rational curves of degree d through m points, right number of points, the same number of points is going to work, but the number will be some finite number, and it will depend on which points you choose. So you'll choose like these points, and you'll get 8. You chose those points, you'll get 10. Those points, you'll get 12. It depends and it can be quite different depending on which points you choose. You can get a computer to go and calculate this for you and see it explicitly. So at least in low degrees. So naive definition of n, d, and r is dependent on the points x1 to xm. Okay, so solution for dimension 2 and 3 which is essentially due to Welschinger, although I'm going to say it in a somewhat different way than he did. This is around 2003-ish. The solution was, well, you want to take into account so let's call this map here a name. This is going to be called EV for evaluation, because I'm evaluating f at the marked points z1 to zm. So take into account the relative orientation of Ev, and this leads you to count some curves with pluses and some curves with minuses. Okay, so a curve, but you can look at the curve and somehow calculate the relative orientation of the evaluation map at that point. And you can sometimes get +1 and sometimes get -1, just like with any degree. You know, in the complex case, there's this kind of canonical orientation, which you always count +1. This is not a surprise. And then in the real case, sometimes you count +1 and sometimes -1. In fact, the total count could be completely negative. So, and then you get, so if you take into account the relative orientation, so then you get an invariant, which is called the Welschinger invariant. Okay, so now for n greater than or equal to 4, however, you need new ideas, okay? This same technique simply has no hope of working. This is kind of surprising, actually. When I first saw this, I was like, that can't be. But when you look at it more carefully, it's kind of a miracle that this works in dimensions 2 and 3, because I kind of was sweeping under the rug that, you know, the problem is, well, I was trying to sort of set the foundation for this before. You know, when you look at this evaluation map, in order to define a degree, you have to compactify to know this degree is well defined, yeah? And when you compactify, of course, you can mess up the orientation. So this, you start with a space which is perfectly well orientable, and then you compactify, it could be not orientable anymore. And there's some kind of incredible miracle which happens in degrees, in dimensions n equals 2 and 3, that somehow when you compactify, things are basically orientable up to some nonsense, but let's not go into it. So basically you can't, so the compactification.
How do you define the invariant again in the previous cases?
So, I mean, you're just counting curves through, you know, whose image passes through a given set of x1 to xm in Cn for the first problem, or Rn for the second problem. And you can think of that as being the degree of this map. So in other words, you look at, if I choose a point in Cn, a bunch of points in Cn, x1 to xm, then I can look at all of the tuples in this space m0, md, which get mapped to those points x1 to xm in this product of Cn's. You just count the number of points over here, and that's, you know, a special example of something called the degree of a map. So these are both smooth manifolds.
Yeah, but I mean, in the real case, you say it's not constant, but then the orientation helps you redefine it. So
right. So if you just count +1 for everything, like just the non-signed count, then you get something which is not independent of which x1 to xm you choose. But if you take into account orientations, like of course you should when you define a degree, then everything just works. Okay.
So this is like a, okay.
So this is not, you know, incredibly surprising, but it should be surprising, okay? Because I've sort of swept under the rug that, you know, something really, really hard had to happen in dimensions 2 and 3 for that to work. I mean, because when you define the map of the degree of a map of smooth manifolds, those manifolds has to be closed and they have to be oriented. And the compactification of M0M is not even going to be relatively oriented. You know, with respect to EV, once n is greater than or equal to 4. So there's some kind of simplification which happens in low dimensions. It's even more complicated than that, to be 100% truthful. Even in dimensions 2 and 3, it's not quite relatively oriented, but somehow you can get around it. You have to sort of like push the boundaries as far as you can go, and then there's some kind of nonsense that goes on there. But basically, it behaves as if it's relatively oriented. But once you go dimensions higher, that falls apart. The relative orientation breaks down. And as you go through points in the compactification, which, you know, loci in the compactification, which could be codimension 1, which you have to go through no matter what, it turns out that your invariant will just jump. And so you get no invariant whatsoever if you do that. Okay, but the general philosophy in this field is that if you don't know what to do, somehow these invariants have a life of their own. So they just work. And so instead of asking, well, I mean, the first thing we asked actually was, can we compute these invariants? So I mean, Welschinger gave a definition for n equals 2 and 3. And let's try to compute it, okay? So I'm not going to write down, so I didn't write down the WDVV equation, which was the key to this work of Gromov-Witten, Kontsevich, etc. But here I'm going to write down, just to give you a really concrete feeling for what's going on here, something called the Open Wdvv equation. Okay, so this is so in order to write this equation down, we need to slightly generalize the problem. So let's define n d n c L0 up to Ln is equal to the number of rational curves of degree d over c passing through, of course, up to equivalence, passing through, well, Ln points, Ln minus 1 lines, Ln minus 2 planes, etc. Okay, and all these things should be defined over C. Okay, that seems like a natural generalization. Instead of just looking at through point constraints, you have to look at lines, planes, etc. And we can similarly do, and this is going to be slightly stranger, but this is going to be the number of rational curves of degree d over r, again up to equivalence, passing through L n k points defined over R. Okay, in other words, k real points, k points in Rn. And the thing is now, when you have a curve defined over R, you can always like complexify it. Just take a real polynomial and think about it as a complex polynomial. And so you can talk about it passing through points or lines or whatever, which are defined over C as well, as long as they're, but it's natural to do things in conjugation invariant. So you have and L, N conjugate pairs of points over C, and L, N minus 1 conjugate pairs of lines over C, etc. Okay, and these, will be either 0 or not 0, depending on whether things, the degree and the number of constraints match up in the right way. So now we can define some generating series, define formal power series, which are going to be generating series. Yeah, so it's going to be this phi of, now this is going to depend on variables capital T and little t0 up to little tn. It's going to be just a way of keeping track of all the possible numbers in one big happy series. So we have t0 to the L0 up to tn to the ln divided by L0 factorial up to ln factorial times n d n c L0 up to ln, sum over d L0 to ln, and omega. So omega is going to depend on, t to the 1/2, and it's going to have also t0 up to tn, and it's going to have an extra variable s, and it's going to be sum over d k at L0 to ln of t to the d over 2, and then t0 to the L0, n to the ln, s to the k, L0 factorial, ln factorial, k factorial, times n d n r k L0 to ln. And now I can state a theorem. Theorem, just do to myself and Sarah Tukachinsky. Well, this is the Open Wdv Equations. It's around 2019. Here they are. So the first one goes, this is a sum over L, partial I. So I'm going to write here partial I is going to be shorthand for partial Ti, and then there's going to also be a partial S. So if we do partial I, partial L, omega, and then partial n minus L partial j partial k phi minus partial I partial S omega partial j partial k omega. That one is equal to this one partial I partial j partial L phi partial n minus L partial k omega minus partial I partial j omega partial k partial s omega. That's one equation. And second equation is we just put s instead of I everywhere where it can go. This is a bit simpler because if you put s into phi, well, phi doesn't depend on s, so that term completely vanishes. That's equation number 2. Indeed, furthermore, equations 1 and 2 and the closed WDVV equation, the one we saw before, which was discovered by Witten and digraphed in Verlind and Verlind, and the classical WDVV, and some additional small properties determine N, D, and R uniquely by recursion if you know the number of lines through 2 points. Okay, so let me give a little, so you're probably wondering what is, so here I should say probably for n odd. Okay, but now is n is, so originally, so what does this mean? The history was for n equals 3 and something similar for n equals 2, we found open WDVV. Okay, then you could use it to compute these invariants. Now, so originally the idea was just to sort of like write down a proof of this, and I have to say, I think, yeah, well, it was kind of irresistible to try to look at what would happen. You know, if you took n, I mean, these equations make sense in any dimension, right? So you can check consistency of 1 and 2 for arbitrary n. Okay, and they turn out to be consistent. Now, this is something very, very surprising. Sort of these equations are extremely overdetermined. So for there to exist in a solution at all is kind of a miracle. And so we knew that there had to exist a solution in dimensions 2 and 3. because there were these invariants, and we could prove that they solved this equation. But then for dimensions higher, we didn't know any invariants, but still these equations had solutions. So the conclusion was there must be invariants, but the question is how you define it. Define.
Sorry, so how didn't you say that n, isn't it difficult to define n and r, d?
Yeah, I mean, we could just write down these equations for n equals 2 and 3, and then we saw that they still have a solution for higher n. So we decided there must be invariants, and then we found them. So we defined invariants. Sarah and I for arbitrary n. Okay, and then finally we proved the theorem. Okay, so I want to say a little bit about what goes into defining these invariants for arbitrary n. Just going ahead and using some kind of degree argument and counting with sign simply doesn't work. Okay, and sort of the alternative here was a little bit radical, but it does work, and it does actually generalize what was previously defined. Somehow, something which seems a lot less elementary turns out to simplify to this very kind of hands-on thing in dimensions 2 and 3 only. So idea of definition. Okay, so first of all, you know, in order to make sense of these things in sort of a modern language, as I sort of mentioned already, you have to compactify everything, okay? So the first thing to notice is that, you know, so Rn, you have it sitting inside of Cn. Well, you compactify, and you get Rpn sitting in Cpn. Okay, and then, well, I was trained as a Gromov-Witten theorist, so I like to think about symplectic geometry and stuff like that. So I immediately look at this and say, well, this is a symplectic manifold. And this here is a Lagrangian submanifold. Okay. So you could say, well, in this particular case, it happens to be fixed by an anti-symplectic involution. And you might or might not think that's relevant. So certainly, okay, so this just means complex conjugation, right? So, but you can make sense of this in an arbitrary symplectic manifold. Well, sort of the early attempts to understand this were, well, we have to use this anti-symplectic involution in a very strong way. Okay, and sort of my doctoral thesis was kind of very much in that mindset. But I always sort of wished that there was a way of doing this without using the anti-symplectic involution too heavily. So there's a general story that if you have a Lagrangian submanifold inside of, so if you have an L inside of X, so you have just any symplectic manifold. Oh, maybe I should say one more thing. So in this case, there's a sort of so what does Lagrangian submanifold and symplectic manifold have to do with all this? Well, there's a notion of, so if you have a rational curve, defined over R corresponds to, well, basically sort of 2 to 1, but let's not go into that, to a J holomorphic disk. So this is a map from the disk to CPN, RPN. And basically the idea is that if you have sort of over on this side, so if you have a Lagrangian submanifold like this, and here's the backboard is X, and then you have so my holomorphic disk is basically some kind of thing like that. Maps the boundary of the disk into my Lagrangian submanifold. So I'm going to generally call this, okay, this is maybe RPN, X equals CPN. I guess I'm basically out of, well, I'm almost have a few more minutes. Okay, then I can sort of, when I have an anti-symplectic involution, I can just reflect this disk through L, basically, and I can use the sort of classical Schwartz reflection principle. This is the image by, so this is sort of, this is the image of U. Let's call this U. This is U. And this is kind of the, I think this is being U bar, if you wish. That's the, you can say that in general, the symplection, the reflection. And then the thing is, you can take U bar and U and you can glue them together and get a map from the projective line, which is essentially a complex, okay, or a complex. It's going to be I mean, it turns out that when you glue them together by the Gaga principle, you have to get just an actual polynomial map. Okay, so you have an invariant map from P1 to CPN, and that gives you a polynomial. It has to be polynomial. Okay, you get an invariant map. So a conjugation invariant map from P1 to Pn, and that has to be, so you glue U and U bar to a conjugation invariant map from P1 to Pn that has to be polynomial by Gaga. So some kind of general principle that when you have compact manifolds mapped by holomorphic maps, they turn out to be. So here I'm talking. I said J holomorphic. It doesn't have to really be the standard holomorphic structure. It can be some slightly more general notion of holomorphic, which gives you a lot of flexibility, which was very important in symplectic geometry. So that's the first stage in this discussion. You turn things into a discussion about disks. And then there's a structure, there's an algebraic structure called the Fukaya A-infinity algebra, associated to, any Lagrangian submanifold. It has to be sort of sufficiently nice, maybe relatively spin, etc. Okay, and then once you have this Fukaya infinity algebra, this Fukaya infinity algebra, its job is essentially to encode the structure of holomorphic disks, J holomorphic disks. Which are exactly these invariants, okay? And then when you have this infinity algebra, there's a notion of a Moore-Cartan element, or what we call a bounding chain. Study Moore-Cartan elements in this Fukaya A-infinity algebra. Let's call this A, AL, okay, and it turns out that up to some kind of natural equivalence relation, there's a canonical element. You find a canonical one up to what you call gauge equivalence. And then there turns out to be a way, if you're given a Markotan element, you can construct a sort of a power series. So you feed, okay, and then you feed B to what you call the superpotential, which actually is just what we define, and you get this kind of omega, which we wrote down very explicitly before. But you do it the other way around. You start with, there's this kind of the superpotential. It's just something you define for an arbitrary cyclic unital A-infinity algebra, and then you can feed it these Markotan elements, and you get back this thing, and it turns out to be a power series. And when you expand it, you get these numbers, okay? And these numbers, in the case when n equals 2 and 3, they turn out to be exactly the ones that I described before. And in higher dimensions, it's not so easy to describe them. It can be done, but I don't have time to do it now. I probably better stop. But then you can use this A-infinity structure and various additional operations that you construct to prove these